starting the surface integrals part 3 with the Green's theorem, and we need to state and prove this Green's theorem. And what is the statement? If P and Q possess continuously partial derivatives in a region R bounded by a curve C, then we need to prove this result. This is the line integral of P dx plus Q dy over the curve C, and that is equal to the double integral of partial derivative of Q with respect to X minus partial derivative of P with respect to Y over the region R, which is bounded by this curve C. Let's start with the proof. Let's understand the region first. Suppose this is your x-axis and this is your y-axis. This is the origin O, right? Let me take two lines, x equal to A and x equal to B, right? And the region is between these two lines, which is bounded by the curve C. Suppose this is your curve C. This region is in such a way that if I take any line parallel to y-axis, because I have taken these two lines which are parallel to y-axis, then if any line that is parallel to the y-axis, this line meets the curve in at most 2 points. And let those points be y equal to phi x and y equal to xi x, where xi x is greater than equal to phi x, right? In another way, you may also take your region in such a way that if you take any line parallel to the x-axis, then this line meets the region which is bounded by the curve C in at most these 2 points. So either line parallel to x-axis or the line parallel to y-axis, it will meet the curve C in at most 2 points. So in the proof, I will be considering this part, and second part we write by similarity, right? Okay, let's start with the proof. Let me write all these first. So it is written that suppose the region is such that any line parallel to either axis, x-axis or y-axis, meets the boundary C in at most 2 points. So here we have taken two lines parallel to y-axis, and if I take any imaginary line, if the line is here, then it will meet these 2 points of the curve C. If the line is here, then it will meet these 2 points of the curve C. So any line that is parallel to y-axis, meets this curve C in at most 2 points, right? Let the region be include between x equal to A and x equal to B, and any line parallel to y-axis with abscissa x, very important. X can be anything between A and B, depends upon where the line is. So those points be y equal to psi x and other is y equal to phi x, where this xi x is less than equal to phi x. Very fine. I have not mentioning here the point at which the line meets, because the line can be here, can be here, can be here, can be here, can be here. It's about any line that will be along the y-axis, right? So that is why I have written here the abscissa x. Now any line which is parallel to y-axis meets the curve C in at most 2 points, which are given by y equal to xi x and y equal to phi x, where this xi x is less than equal to phi x. So here xi x is less than equal to phi x. Thus, boundary C is split up into two arcs C1 and C2. So here we can split this boundary C into two arcs, that is this one from A to B. Let this be the arc C1, and the other one is from B to A in this direction, and let this be arc BC2, right? Now to prove this result, let me start with the right hand side and taking this term first. So this is a double integration over the region R, partial derivative of P with respect to Y, dx dy. That is equal to the double integral of partial derivative of P with respect to Y. I'm writing here dy and outside dx. Why I have interchanged these two? Because the limits of x are constant, and whenever you are having the constant limits, that integral should be outside of this inner integral, right? And what are the limits for y? It is from xi x to phi x. Very fine. Okay. Let's integrate this integrand with respect to y. So on integrating the integrand, we are getting p depending upon x and the value of y. We have to put the upper limit first. So that is phi x, right? Minus p depending upon x and y. And now writing the lower limit of y, that is xi x. Splitting this integral. So this is the integration from a to b for the first term. Dx minus integration from a to b for the second term. Right? Okay. Now what is phi x? This point lies on the curve 2. Right? This phi x point lies on the curve C2. That is, the curve is from B to A. Right? So I am having here the integration from A to B. If I write this as from B to A, the sign changes. So this is Px comma phi x dx minus the integration from A to B, and phi x, this point lies on the curve C1. This point lies on the curve C1, and C1 arc is from A to B. So this integration remains as it is. Very fine. Okay. Now I can write this integral as, because this integral is from B to A, so this is for the curve C2 and this integration is for the curve C1. And writing this phi x to be as y only and this xi x also to be as y. So this is equal to minus the integration over the curve C2 pxy dx minus the integration over the curve C1 pxy dx. Taking minus outside, we are getting the sum of these two integrations. So now I can write this complete to be as integration over the curve C, the complete boundary C, because this C is equal to sum of these two arcs, right? So this is equal to minus the integration over the boundary C pxy dx. And the left hand side is the double integration over the region R, partial derivative of p with respect to y, dx dy. Please mark this as 1. Similarly, we can get the result for the another part, for this integral to be as the double integration over the region R, partial derivative of q with respect to x, dx dy is equal to the line integral over the boundary C, qxy dy, and marking this as 2. So from 1 and 2, if I subtract 1 from 2, writing here the right hand side first. So this is the integration over the boundary C, qxy dy, and when subtracting this we get here the positive sign. The integration over the boundary C, pxy dx, to be equal to the double integration over the region R, partial derivative of q with respect to x dx dy, minus the double integration over the R, partial derivative of p with respect to y dx dy. So this is q dy minus p dx, that is equal to the double integration over the region R, and writing here partial derivative of q with respect to x minus partial derivative of p with respect to y, and writing here dx dy for these two. So hence Green's theorem has been proved. Okay, thank you. Stay blessed.